Hi all. In this video we're going to cover chapter 7.3, and that's simplifying radical expressions. And last year Miss Griffith taught you all about simplifying radical square roots, I should say, square roots in geometry. So this year we're going to expand that to third roots or cube roots, the fourth roots, fifth roots, and so on. So the very first thing I want you to write in your notebooks is the product rule for radicals. And the product rule states if the nth root of a and the nth root of b are real numbers, then the nth root of a times the nth root of b is the nth root of a times b. So what we're going to look for when we're combining radicals together is we're going to look at the index of the two radicals, and if they are the same, we can combine it under one radical with that same index, and we can multiply the two terms under those radicals. So let's go ahead and practice that. We are going to multiply radical 5 times radical 7 and combine it into one radical, and you notice they're both square roots, so they have the same index. So that would be radical 5 times 7, which is radical 35. That does not reduce any further. Radical 35 does not have a perfect square as a factor. All right, so the next example, radical 13 times radical z is going to be radical 13z. That does not reduce any further. 13 is a prime number and does not have a perfect square as a factor. Now we have the fourth root of 125. So let's take a look at the fourth root of 125 times the fourth root of 5. They have the same index, so we're going to go ahead and combine them under one radical sign. So it's the fourth root of 125 times 5, which is the fourth root of 625. And if you know your perfect fourth roots, which I'm sure some of you guys do, the fourth root of 25, let's go ahead and factor 25. We're looking for groups of 4 in order to simplify this. I know 5 goes into that because I multiplied 5 times 125. I also know 5 goes into 125 25 times, and I know 25 is 5 times 5. So we're looking for groups of 4. In Miss Griffith's class, you were looking for groups of 2. This index says we're looking for groups of 4. We have a perfect group of 4. So remember, with a square root, you brought one of those out. In each group, you brought one of those out and you multiplied. For the fourth root, you're going to bring one of those out. We have nothing left under a radical sign, so we have simplified it as best we could. The next one, we're looking for cube roots. We have 2 cube roots being multiplied, so let's combine them under one cube root sign. 5 times 3 is 15, x squared, and y. All right, 15 does not have a perfect cube root as a factor, so we can't simplify that. We don't have a group of 3 x's, we only have a group of 2 x's, and we only have one y, so that's as simple as it gets. Now, I'll page back, so if you need to copy any of those examples down, why don't you do so now? All right, we are going to move on to the quotient rule. The quotient rule states that if you have the nth root of a divided by b, you can split that up into the nth root of a divided by the nth root of b. It also works backwards. If you have the nth root of a divided by the nth root of b, you can combine that, if they have the same index, into one root of a fraction. So let's use our quotient rule to simplify some of our fractions down here. Let's simplify the first one, and we're going to split this up into the square root of 36 over the square root of 49. And we know that 36 and 49 are perfect squares, so our answer is 6 over 7. The next example, we're going to split up as well, the square root of z over the square root of 16. That gives us the square root of z. 16 is a perfect square. Square root of 16 is 4. Now let's take a look at our last two examples here. We're going to do a cube root. And we're going to split that up and see if we can simplify. The cube root of 125 over the cube root of 8. We know that 125 factors into 5 times 5 times 5. That's a perfect group of 3. So we're going to pull a 5 out. We know that 8 factors into 2 times 2 times 2. That's also a perfect group of 3. We're going to bring that 2 out. We have nothing left under the cube root signs for either in the numerator or in the denominator, so we are done. So now let's take a look at the fourth root. We're going to split this fraction up into the fourth root of 5 over the fourth root of 81x to the 8th. All right, so what can we simplify? Well, I know there's no fourth root of 5, so I'll write that in my numerator. But now let's talk about factoring 81 and x to the 8th. 81 factors into 9 times 9, and 9 factors into 3 times 3. So we end up with a perfect group of 4. So we'll pull one of those out of our radical. So we have 3, the fourth root of 8 to the x. I say we can still simplify that because 8 to the x is a group of 8 x's. X, 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 x. All right, and we're looking for groups of 4. So let me circle a group of 4 here and a group of 4 here. We have 2 perfect groups of 4, so when we pull them out, we're going to get an x times an x, which is an x squared. Okay, so now we're going to put all those rules together and we're just going to start simplifying. We're going to be simplifying fools. So the very first one, we are going to look for the square root of 98. Well, it just so happens that I know my perfect squares, and I know that 98 is 49 times 2. And I chose 49 because 49 is a perfect square and it is a factor of 98. So I can then use my product rule to separate these two, and I get 7 radical 2 as my answer. If I did not know that 49 was a factor of 98, I could go ahead and take 98, the square root of 98, and start factoring it. I know that 2 goes into 98. And when I divide that, I get 49. I know that 49 is 7 times 7. I have a perfect group of 2. I would pull that out, and I still have this 2 remaining under my radical. I get the same answer. So if you know your perfect squares, your perfect cubes, your perfect fourth roots, it makes your simplifying of your radicals much easier. So let's go ahead and take a look at 54, the cube root of 54. Well, my perfect cubes, let's walk down the list of perfect cubes. 1 cube is 1. 2 cubed is 8. 3 cubed is 27. And 27 is a perfect cube that goes into 54. So I'm going to rewrite 54 as 27 times 2. I know that the cube root of 27 is 3. So I end up with the cube root of, or I end up with 3 times the cube root of, sorry, that's a 2 in there. 3 times the cube root of 2 is my answer. Again, you could go ahead and factor 54 and find perfect groups of 3 if you need to do it that way. Okay, so now let's take a look at 35. And let's take a look at some of those perfect square roots. We know perfect squares are 1, 4, 9, 16, 25, 36, and none of those go into 35. So my guess is that 35 does not reduce. If I factor 35, I get 5 and 7 as the prime factors. I don't have any groups of 2, so 35 is, or the square root of 35 is already simplified. All right, so now let's take a look at our next example. I know my perfect fourth roots, but I know some of you don't. So let's walk through our factoring method. When we factor 243, I know that 3 goes into 243, and let's see, it goes into 24 8 times, and it goes into 3 1. So that's 3 times 81. I also know that 81 is 9 times 9. So let's factor our 9s down into their prime factors. I'm looking for a perfect group of 4, and I found it right here. I still have a 3 up here. So when I reduce this and simplify it, I will pull 1 3 out of my perfect group of 4, but the other 3 remains under my 4th root symbol. All right, the biggest mistake here for any of these examples is not to write your index here. You need to bring that index down and make sure that you write that in your answers for both this one and in this example here. If we left that as a square root of 2, if we forgot our index, it would not be correct. So let's simplify our next set of problems here. Now we have variables in our problems. So in the first example, we're looking for the square root of 36, which I know that is 6 times the square root of z to the 7th, but I can simplify my z's. I have 7 z's, and if I wrote those out, I'd be able to group them in groups of 2. I have 3 groups, so I'll bring out 3 z's, and they are going to be multiplied together, so I get z cubed. But I have 1 z that's left over, and he stays under the radical. The next example is a cube root, so let's take a look at the cube root of 32. I'm going to go ahead and rewrite 32. I know the biggest cube root that goes, or the biggest perfect cube that goes into 32 is 8. If I do my perfect cubes, I get 1 8, 27, 64, and so on. I know 8 is a perfect cube that goes into 32, and I'm going to write it as 8 times 4, p to the 4th, q to the 7th. I can take that cube root of 8, which is 2. So I'm done with him. How many perfect groups of 3 do I have out of 4 p's? I have 1 group of 3, so I'll bring out 1 of those p's. And how many groups of 3 do I have in 7 cubes? I have 2 groups of 3. So I have q squared. And now what is left over under that radical? Well, my 4 is left over. And out of my p's, I took out a group of 3, so I have 1 p left. Out of my q's, I took out 2 groups of 3, which is 6, so I have 1 q left. Okay, let's take a look at the 4th root of z, to the 11th. We already learned that the 4th root of 81 in one of my other examples was 3. But if we wanted to walk down the perfect 4s, I guess, you would get a 1, 2 to the 4th is 16, 3 to the 4th is 81. 81 is a great factor of 81, right? So we would get 3. And how many groups of 4 do we have in z to the 11th? We have 2 groups of 4, so that's z squared. And we have 3 that are left over. So if we actually wrote out z to the 11th 11 times and took out 2 groups of 4, we would have 3 left over. So we end up with a z cubed under a radical. Okay, these are our last set of examples that we're going to do. And here we're going to go ahead and use our quotient property, and we're going to combine our radicals to make it easier to reduce. So here we have radical 80 over radical 5. They have the same index, so I'm going to do 80 divided by 5. I combine that into one radical. I know that 5 goes into 80 16 times. So I'm left with the square root of 16, which I know is 4. Makes it a lot easier. Okay, so here I have the square root of 98z over 3 times the square root of 2. So that 3 on the bottom can be written as 1/3. I'm going to combine this square root and this square root under one square root. See if I can get this simplified. I know that 2 goes into 98 49 times. And I have a perfect square in 49. So I am going to get 7/3 times the square root of z. Okay, final answer right here. Let's do the same here. We have 2 roots, one in the numerator and one in the denominator. They both have the same index, so let's combine them under one radical, one cube root. We have 40x to the 5th, y to the 7th over 5y. Let's reduce what we have here. So we get 5 cube root of 8, x to the 5th, y to the 6th. We're looking for perfect cubes. So I know 8 is a perfect cube. Cube root of 8 is 2, so I get 5 times 2. I have one group of 3 in those 5 x's, so I'll pull out 1x. I have 2 groups of 3 in y to the 6th, so I'll pull out 2 of those y's. And what's left over? Well, all my numbers, that 8 is gone, it was a perfect cube. I have 2 x's left over, and I have no y's. So let's just simplify out here. 5 times 2 is 10x, y squared, cube root of x squared. Final answer. One last problem here. We have 2 roots in our fraction. They have the same index. So let's combine them under one radical sign. And let's simplify what's underneath the radical first. Let's use our quotient property for exponents to simplify this. So we get 3 times the 5th root of 64. 9 minus a -1 is x to the 10th. 8 minus 2 is 6. So now all we have to do is simplify that. The 5th root of 64, let's see, 2, 4, 8, 16, 32. 32 is a perfect, is 2 to the 5th. So we can pull out a 2. How many groups of 5 do we have in 10x's? We have 2 perfect groups. How many groups of 5 in my y's? We have 1 perfect group. 2 to the 5th was 32. So that's 32 times 2. So we have a 2 left over here, and we have 1y left over here. So I think we have a radical simplified. Let's multiply our numbers on the outside. 6x squared y times the 5th root of 2y. And that's how you would simplify that. Okay guys, the rest of the class is for you to do your homework if there's any time left. Remember, there's 2 sections of homework due tomorrow. Enjoy!